Hi everyone. So today I'm going to be talking about flexural strike slip basins. And this is a kind of new type of basin we're suggesting from numerical modeling of seismic reflection data from the East Andaman Basin. And so this talk will actually be a little bit more broad than this. I'm going to start by talking about the Fastscape aspect coupling, just go over kind of how this works and some of the features that's included with it. And then from there, I'm going to go on to some examples of the coupled models. And the bulk of this will be on this strike slip sedimentation. But then after that, I'll briefly talk about some of the work other people have been doing on asymmetric mountain ranges. So to start, I want to talk about Fastscape. So Fastscape is a surfaces processes code by Jean Braun. And so what this does is it deforms a surface based off of a few different laws. One of these being the stream power law, and this is really what allows rivers to incise into mountains. So as you can see this image here, we have rivers eroding into the mountain, and this is from our stream power law. And then kind of combined with this, we have sediment deposition. So some portion of the sediment that is eroded from this law can then be deposited, which we can see down here. And there's also then hill slope diffusion and marine processes. And so kind of how this works is we have this equation up here, and we have our change with height over time will be due to a few different components. This first one, U, is our uplift rate, and this and also advection will be velocities that are supplied from aspect. And then the second term here is to do with our stream power law. So we have A, which is our drainage area, and S, our slope. And then KF is our river incision rate. So this just tells us how fast we erode these mountains and how fast these rivers incise into them. Then we have this third term, which is, there's a lot going on here, but the main thing is this is just how much of the sediment gets deposited. And for this, we have this G term, which you can change. And this just tells you how much will be deposited, although in no case can all the sediment be deposited. So there'll always be some that gets left through the system unless you have marine processes turned on. And then this final term is our hill slope diffusion. So for this, we have our KD value, which is our deposition coefficient. And for surface processes, this can be for bedrock and sediment. And then for marine, you also have two additional ones for sand and shale. So then how Aspect uses this is you can call Fastscape as a mesh deformation plugin. And when you do this on the first time step, Aspect will send its surface, so all the heights and the velocity components from the surface, and it'll use these to initialize Fastscape. And from there, we'll save this initial Fastscape surface. And then we'll run Fastscape with these different processes that'll deform this surface. And from there, we'll take a look at this new surface and find the difference with our initial surface and divide it by our aspect time step to give us a z velocity at each of these nodes. And we'll then send this velocity back to aspect, which will update the surface to match what we see in Fastscape. So that's on the first time step, but every other time step, there's cases where your Fastscape will be more resolved than aspect, and we don't want to lose this resolution by resending these heights. So in these cases, we'll just send the velocity components, but other than that, everything will work kind of the same. We'll update Fastscape with these velocities. We'll save this initial surface, run Fastscape, get our Z velocities, and then update the aspect surface. So some of the capabilities that you can use with this coupling now. So all those processes I mentioned, the stream power law, hill slope diffusion, advection, marine processes, these can all be applied to 2D or 3D aspect models. And for 3D aspect models, the Fastscape surface will match what you have in aspect. And then for 2D models, you would pick a Y extent. So this here is an example of a 2D rift model. So you pick this Y extent, and then the aspect value is just copied to every node along this Y extent. And then when you want to send this back to aspect, you have two options. You can either take the center slice from the Fastscape model and assume that that's your aspect surface. Or the second one is you can average all these points back together to get your value for aspect. And the next thing, as I mentioned earlier, Fastscape really likes to have a resolution of 1 kilometer or less. And for 3D aspect models, this sometimes isn't possible. So we can refine Fastscape above aspect so you can still get a good Fastscape resolution. And kind of similar to this, since aspect has this adaptive mesh refinement, you may get different cell sizes at the surface, as we can also see in this 2D model. And we wanted to make sure if you get these varying cell sizes, this doesn't mess up your Fastscape mesh because it has to have the same resolution everywhere. So for this, we always assume that our Fastscape surface is resolved at least at our highest aspect cell size at the surface. And then for, you tell the coupling how many different cell sizes you expect to see at the surface. And then for like this lowest resolved one, we just make sure there's enough interpolation points between it that it can still fill out this more resolved Fastscape mesh. And then also, because a lot of times you need to restart your aspect models, we didn't want to lose resolution and reinitialize Fastscape with these this low resolution aspect surface. So whenever aspect creates a restart file, we will also save the heights and basement values for Fastscape so that when you restart aspect, Fastscape can restart along with it at the same higher resolution. And one other thing implemented is ghost nodes that surround the aspect boundary. And so the main point of these is that Fastscape will have some boundary effects that we don't want to see in our aspect models. So we have our aspect boundary here, which would be this white, and then we just add one additional layer of nodes in Fastscape so that anything that occurs at the boundary, we don't actually see in our aspect model. And then, so these are updated every time step where we'll get values from aspect for these points along its boundary. And then we just take these points and we copy all the velocity components and heights to the corresponding ghost node. And then for corners, of course, this will go to all three. And then this gives us a little flexibility what we can do with these boundaries that can then be put into aspect. And so one example of this is we wanted to have models where we had an off-model source of sediment. And so Xiaoping mentioned something we could do for this is through the diffusion term. So if we have a point here and we say we want to have a certain sediment flux, we can then, we know our KD value. And so we just need the slope to determine what the sediment influx is. So we find the slope at this point and we decide how much we need to elevate this to get the needed slope for the sediment flux we want. And the second use we have it is to have periodic boundary conditions in Fastscape. So Fastscape can already be periodic in the stream power law, but for advection and diffusion, it's not periodic. And especially with aspect models and oblique rifts and such, we wanted to have these periodic advection. So in these cases, if we say these boundaries are periodic, then at these boundary nodes, we'll actually check the velocities. And so if we see at this point that our velocities are actually going this way, like they are here, then we say in this case, we're periodic. So then we take all these values and we actually just copy them over to this side. So then if we have, say, a mountain or something being advected off this side, all the values will be sent here and we'll just kind of copy and start having the mountain appear on this side. And so this is just an example that was just to test these boundaries, and I'll start playing it now because it's kind of long. So we wanted to make sure that in our Fastscape an aspect, once we started setting a mountain through these boundaries, that it would keep its direction, shape, and everything like this. So we just set up the simple model and aspect that just moved this mountain around with really nothing else going on, just to see how it would react going through these boundaries. And so this shows the Fastscape surface, but if I plotted the aspect surface too, we would just see the similar thing. And so our mountain is diffusing over time from just numerical diffusion from the advection scheme. But we do see that it keeps its shape and everything when it goes through these, and it keeps its direction. And then just for fun later on, I also wanted to send it into a corner just to see what would happen. Because again, this is unrealistic and we just had every boundary periodic, which it wouldn't happen, but it shows that at least we're not like duplicating our mountain or it's going in different directions or anything like this. And so that's really what I wanted to go over for the overview of the Fastscape coupling. And next I wanted to show some examples. So first I'll talk about this sedimentation along a strike slip fault and comparing this to the Andaman Sea. And then next I'll go into some work Sasha's been doing on orographic controls and asymmetric mountain ranges. And then also show some more preliminary work where Mikhail has applied this to his 2D subduction models. So to start, I want to talk about how basins form. Basins form as sediment fills tectonically created accommodation space. And the way the space is created kind of falls into two different types. You have lithospheric thinning and thermal subsidence, maybe at like a rift zone, and this can create space for these basins to fill. Or the second one is if you have a sufficient load, you can actually flex your lithosphere and again, create this accommodation space. Now, as we're talking about pole apart basin or strike slip basins, I want to talk about polar apart basins. So polar apart basins are really the only known type of basin that forms along strike slip faults. And this is the type of basin that forms due to this lithospheric thinning and extension. So here I kind of have two examples showing this. On the left, we have this Dead Sea fault. And so along this fault, you can see areas where we have like the Dead Sea, the Sea of Galilee, but there's a slight offset and we get the formation of these seas. And then over here, we have the San Andres fault, where again, you can see we get a lot of different small offsets between the strike slip faults. And within these offsets, we begin to form these pole apart basins. So to go over how these pole apart basins actually form, so we have these two offset strike slip faults. And as they kind of propagate forward, they have compression at the tips, which creates local highs that can then provide sediment for the forming basin. And then inside these two, inside the offset, we actually get extension because of the direction these are propagating. So because of this, we begin to extend the central region and create this basin. And then over time, as this motion continues, we'll begin to extend and lengthen our basin. So what we end up is with a kind of long, thin basin where we have a depicenter that is located between the two strike slip faults. And then the width of it is kind of confined to these strike slip faults as well. So again, the reason I want to bring this up is these are really the only type of basins we see along strike slip faults, but there's not really an example of one of these flexural strike slip faults forming at or along a flexural strike slip basin forming along a strike slip fault. And we think we do have a good example for this in the Andaman Sea, and it's something that we decided to try and model. So that brings me to the study region, the Andaman Sea, which is located off the coast of Thailand. And this is an area, it's a back arc spreading region that formed during the Cenozoic. And so initially it had this extension, but in the early Miocene, there was a shift to more strike slip motion. And from this, multiple major strike slip faults started to form in the area. So this, like the Sagaing fault in the north and some faults bounding on this side. But for this study, I really want to focus on this fault to the south down here, which is now inactive, but it's called the South Sagaing Fault, and it was active for about 5 million years. And what's interesting about this strike slip fault is that it actually formed in the previous necking zone left over from this time of extension. So in this next area is just going to be on this box labeled B here, which will show us a closer look at this fault. So here we have the two-way travel time, just to give us an idea of the sediment thicknesses in the area. And so here is our South Sagaing Fault. And then on top of this is the basin that we're going to be looking at, this East Andaman Basin that covers this fault. So to kind of characterize this basin, we actually see it on both sides of the strike slip fault. And on this western side, it's relatively uniform and not very thick. And then though when we go on this eastern side, we see this depicenter of this basin, which is located right along the fault trace. And for this side, we actually have it thick right next to the fault, and then it actually thins eastward towards this Murgoi Ridge. And then so this Murgoi Ridge is an interesting feature that was actually experiencing uplift at the time this fault was active. And so it's thought that is likely a sediment source for this forming basin. And so the one thing I want to make note of is that we have this basin that exists on both sides of the fault, and then it has depth center located along this, not necessarily in between two strike slip faults. So it doesn't really fit this classic pole apart basin that we were talking about earlier. And our colleague Chris Morley came to us with the idea that maybe this is caused because we had this localized sedimentation coming from this Murgoi Ridge, and this was somehow causing subsidence and creating this basin in this thin lithosphere. So with the coupling, this is now something that we could test. So we came up with our initial hypothesis, which was that strike slip fault is acting as a weak zone where focused sedimentation can force substance and the creation of flexural accommodation space. And if this is true, the things we wanted to ask was, how does variable sedimentation rate and the pattern of this sedimentation affect subsidence? And then because this is in a previously necking zone, how important is the lithosphere thickness, and can we still get this in normal lithosphere? And then finally, does the strength of the fault play a role in what these basins look like? So to test this, we set up a model that has both a surface component at the top here and a tectonic component. So for the tectonic component, we have a viscoplastic aspect model where we have 40 kilometers of lithosphere and then 8 kilometers of crust divided between upper and lower. And then we perturbate our LAB by 10% just to give an area for our strike slip fault to initially localize. For boundary conditions, on the front and back, we do periodic to assume we have just an infinitely long strike slip fault. And then on the eastern side, we do no slip in X, Y, and Z. And on the western side, we similarly do no slip in Z. Then we add a very small 0.2 millimeter per year extensional component in X just to avoid compressional pop-ups. And then for strike slip motion, we prescribe 2 centimeters per year in Y. And then for the bottom boundary, we have lithostatic pressure just so any sediment that's added can have outflow from the bottom. And then on top of this, we have a surface model, which we wanted to keep pretty simple. So we just assume the whole thing is underwater and that sediment is moved through marine diffusion. And then we add sediment to the system in 2 different ways. The first is that we just add an even sediment rain all over the model at 0.2 millimeters per year. And then the second one is that we input sediment from the side at 40 meters squared per year. And then so Fastscape will have 2 different surfaces that we get from this. We'll have our topography at the top, which will be the combination of the velocity sent from aspect and what these surface processes do. And then this basement, which will just be changes from the velocity sent from aspect. And then we assume that difference between these 2 would then be our resulting basin. And so we also set our aspect model surface to fixed sediment. So we'll actually see the same thing where the basement and aspect will deflect based off of these velocities, but because the surface is different, we'll still get the sediment package. And then we run this model for 10 million years total, where the first 5 million years, we're syntectonic, we have strike slip motion and sedimentation. And then after this, we stop both the sedimentation and the strike slip motion, and we run for another 5 million years just to kind of let the surface even out. And so first I want to show the surface model showing this. So this is our model in Fastscape, and you can see here we have the uplifted ghost nodes to supply the sediment. And so I'll start playing the video. So you can see we get a lot of sediment coming in from this side, and then this is where a fault would be. And here we get a lot of localized substance on the side with more sediment. And then this continues until 5 million years where we stop our strike slip motion, and then the sides become coupled again, and there's some substance, but not as much, and they sink more evenly at this point. And then in the end, we can kind of see a resulting basin that's much thicker on this eastern side that received more sediment while the fault was active. And so next I wanted to show the same thing in the tectonic model. So this is just a center slice of the top 30 kilometers of the model with these red arrows representing the subsidence rate. And so by 0.5 million years, you can see we start to form a sediment hill on this side, and we've also localized our deformation on this thin strike slip fault, and we have a small amount of subsidence. Then over time, our shear zone kind of starts to widen, and we get more sediment on this side, which is causing this eastern half to subside much quicker relative to this western half. And then at this point, we stop our strike slip motion, and our sediment hill starts to diffuse out through the model. And so by 10 million years, we have a basin like in our surface model where we have much thicker on this eastern half than this western half. And so this is what we then want to compare to the East Andaman Basin. So then here is an interpretation from a seismic section of the East Andaman Basin, and then C here is part of the seismic section. And so we have our South Sagaing Fault here in the interpretation, and then here in our the actual seismic section. And then with this, we have tan, which is the syn rift or syn kinematic section, and the brown, which is our post kinematic section. And so like we kind of saw in the two-way travel time, we see here that on this western half, we have a pretty uniform and relatively thin basin. But once you get on this eastern half, we have a basin that's much thicker right next to this fault. And then it starts to thin to the east towards the likely sediment source, the Murgoi Ridge that we would have over here. And so we see a very similar thing happen in our reference model basin. Of course, we don't just have a very localized fault like here, but we have this shear zone. And then on the western half of the shear zone, we have a relatively uniform thin basin. And then on this side that had a lot more sediment while the strike slip fault was active, we have this thinner basin or thicker basin that then thins towards the east, although not quite as significantly as the real basin, but it thins towards the sediment source where we're pushing in this sediment. And so the next thing we wanted to ask was, well, we want to answer those three questions. How does the change in sedimentation affect this, the lithosphere thickness, and the fault strength? So the first one I'm going to talk about is increasing the sedimentation. For this, we kept the same sediment rain for every model, but then we changed the amount we put into the side from 0 all the way to 60 meters squared per year. And what we see is why there's some effect from pushing more sediment on this side on the western half. For the most part, as the sides are pretty decoupled, just the eastern side subsides more and more as it gets this more sediment. And once we get to having completely even sediment, we see that both sides subside similar. So we get a different kind of basin shape where we have both sides thickest next to this fault, and then they thin away from the fault, forming kind of a synformal basin. So from this, we kind of say that there's two different types of basins that can form based on the pattern of the sedimentation. If we have kind of axial or even sedimentation, we can get this synformal type of basin. And then if we have asymmetric sedimentation, we of course get this more asymmetric basin. So the next thing we wanted to look at was how lithosphere thickness changed this. So for this, we varied our lithosphere thickness from 30 to 60 kilometers. And kind of as expected, as you increase your lithosphere thickness, you can no longer accommodate as much of this flexure. So there's less flexure and more of this sediment is just accumulated above this initial surface. And so what this really tells us is that you do need to have previously thin lithosphere, because by 60 kilometers already, we're only forming a small basin. So if you're in normal lithosphere, it's unlikely that the sediment can force this flexure. And then the last thing we looked at was changing the fault strength through the friction angle weakening, where we went from 25% weakening all the way to 99% weakening. And the main thing you see for this one is that as we increase our weakening, our deformation becomes more localized and we get a thinner shear zone. And then this also leads to a more drastic change between the two basins. So when we have not much weakening, the sides are much more coupled, so they both kind of subside the same amount. And then as we have more weakening, they become more and more decoupled. And so just for the conclusions for this, if we're in a place where there's previously thin lithosphere and we form a flexural strike slip basin in here, or we form a strike slip fault in here, then sediment can form one of these flexural strike slip basins. And for this, the fault kind of works as a weak zone that decouples the two sides. And because of this, each side can respond relatively independently based on the sediment load it receives. And then from this, two types of basins can form based on the way sediment is put into the system. If it's axial or even sedimentation, you can get a synformal basin. And if it's asymmetric, you can get an asymmetric basin. And then this East Andaman Basin is an example of one of these asymmetric flexural strike slip basins. And so that's mostly what I talked about for that. But as that was a rather simple use of the coupling, we were only using the marine diffusion and really nothing else. I want to talk a little bit about work that Sasha's been doing on asymmetric mountain ranges. So for this one, the motivation for this is that when you look at the Andes, you get these asymmetric mountain ranges, and that this is maybe due to orographic controls on erodibility. So to test this, he set up a 2D aspect model that has compression, and it's just a 2D crustal aspect model with compression. And so then he applies to this two orographic controls to the surface model. The first is to assume that once we reach an elevation of 500 meters, that we have a certain wind direction. So because of this, this eastern half will erode faster. And so this western half then is reduced, the KD and KF are reduced by half to have lower erodibility. The second is that when an elevation of 2,000 meters is reached, we assume that there's just less precipitation and so also less erodibility. So again, the KD and KF are reduced by half. And so again, first I'm going to show the surface model of this. So we initially get a mountain block that's uplifting pretty symmetrically. And then as our erodibility changes, we get a shift in the drainage basin to the west. And then we start to see actually our whole mountain range begins to shift towards the east as this happens. And so in the end, we have this asymmetric mountain range that's shifted to the east, but it's kind of hard to tell exactly what's happening from just the surface model. Sorry. Okay, so next I want to show the tectonic model. So this is going to show the uplift rate in this tectonic model. And so to start, we get our initial uplift block, and then we would have a fault forming here. And then as we begin to increase erodibility on this side, we begin to shift to this side as two, and we start to form a new fault on this over here. Oh. So in this, as this continues, we get erosional unloading on the side, which actually increases the uplift rate on this side relative to the western side. So we start to getting a tilting of our mountain block as it shifts to the east. And so I want to show this because I think it's just a really cool example too of how much these surface processes can affect the underlying tectonic model. And then also, since Mikel is then working on these fully 2D subduction models of the Andes, we asked him to try and apply these surface processes and these orographic controls that Sasha did to his subduction model. So here's a video of one of his subduction models, and this one is without the surface processes, but I just wanted to show it first to give you an idea of what's going on underneath the surface model. And so I'm not going to do too good of a job explaining this, I'm sure, but main things I want you to pay attention to are the buckling of the slab that occurs once it gets into this transition zone, and how this affects the trench migration speed. So you can see initially we have some flat slab, and this slab starts to reach the transition zone. And we have migration of our trench, but then this stalls for a bit. And then once we start to get this buckling that's happening down here, you'll see the phases of where we get trench migration stalling here. And then at a certain point, it starts migrating again, and then another stalling phase. So then this is a preliminary model where he just threw on these surface processes with these orographic controls. And so this bottom part won't change, but you can see that there's still this buckling that's happening in the transition zone. So we'll see how this looks then at the surface. So we initially begin to form our mountains, and then once we get faster trench migration, our mountains quickly erode away, and then stalling and more mountain building. So it's kind of cool to see. It seems that with these different phases of trench migration and stalling, we get different phases of mountain building as well. And then for this model too, this doesn't include that sediment, but it'll be interesting in the future to see when we can also have this sediment composition in an aspect from the erosion from this fastscape, and see how this affects these subduction models. But I think that's about it. So any questions?
Thanks a lot, Derek.